We used to think LHS 475b was just a frozen, dead graveyard drifting through the cosmos. But the James Webb Space Telescope just detected something impossible: a massive chemical spike of sulfur dioxide. This isn't just gas. It's the heartbeat of a world that is screaming with active volcanic life. Before we can understand the silence, we have to appreciate the shout we were expecting to hear. The James Webb Space Telescope, or JWST, isn't just another telescope. It's a masterpiece of ingenuity, a $10 billion observatory designed to capture faint, ancient light. Its 18 gold-plated hexagonal mirrors give it a light-collecting area over 6 times larger than Hubble. But for our story, its real power lies in what it can see. JWST is an infrared telescope, meaning it sees light that's invisible to us, the light of heat and of distant, stretched-out wavelengths. This is crucial for studying exoplanets. When a planet passes in front of its star, a transit, a tiny bit of starlight filters through the planet's atmosphere. Think of it like cosmic fingerprint analysis. Different molecules in the atmosphere absorb specific colors of light. By capturing the spectrum of that starlight, JWST can see which colors are missing. A dip in the spectrum might mean water vapor. Another could signal methane. These are called absorption lines, and reading them is how we decipher the makeup of a world light years away. For decades, this technique, known as transmission spectroscopy, was mostly limited to the puffy, sprawling atmospheres of gas giants. Their sheer size made them easier targets. But what we truly craved were the small, rocky worlds like our own. The challenge was immense. The atmosphere of an Earth-sized planet is a gossamer-thin veil. The signal it leaves in the starlight is almost infinitesimally small, a whisper that was lost in the noise for previous telescopes. But JWST was built to hear those whispers. Its sensitivity is so exquisite that it can detect the subtle dimming caused by an Earth-sized atmosphere. This was the promise of a new era, the age of rocky exoplanet characterization. For the first time, we had a tool powerful enough to not just find Earth-sized planets, but to analyze them, to sniff their air across trillions of miles and search for the chemical imbalances that could hint at geological activity or even life. The astronomical community was buzzing. We had our best detective yet, and now we just needed a suspect. With thousands of confirmed exoplanets, the universe has no shortage of options. But if you're hunting for an atmosphere on a rocky world, you need a specific kind of target. You want a planet that's relatively close, so its signal isn't too faint. It needs to be transiting its star, and ideally, you want it orbiting a small star. That might sound counterintuitive, but it's about proportions. A planet crossing a small star blocks a bigger percentage of that star's light, making the atmospheric signal stronger by comparison. That's why many of JWST's prime targets are found orbiting red dwarf stars, the most common type of star in our galaxy. And so, astronomers sorting through data from NASA's Transiting Exoplanet Survey Satellite, or TESS, flagged a candidate of huge interest. It was a system just 41 light-years away in the constellation of Octans, a cosmic stone's throw. The system was named LHS 475, and the potential planet looked small and rocky. This was exactly what JWST was built for. A research team, led by astronomers at the Johns Hopkins University Applied Physics Laboratory, booked time on the new telescope to take a closer look. On August 31st and September 4th, 2022, JWST pointed its golden eye toward the star and waited. As the planet passed in front of its red dwarf sun, the telescope's near-infrared spectrograph, NIR-SPEC, collected the data. The result was immediate and spectacular. The telescope confirmed the planet's existence with total certainty. It was there. And its size was astonishing. The data revealed a world that is 99% the diameter of Earth. Not a gas dwarf, not a mini Neptune, but a true terrestrial twin in size. But the similarities mostly end there. LHS 475b zips around its star in just 2 Earth days. It's closer to its star than Mercury is to our Sun, and is a few hundred degrees warmer than Earth. This extreme proximity also means it's almost certainly tidally locked, with one side in perpetual daylight and the other in endless night. This wasn't a candidate for a gentle Earth-like habitable world, but that wasn't the main goal. The goal was to find an Earth-sized rocky planet with any atmosphere that JWST could study. And, given its size and temperature, scientists had good reason to expect one. A planet this size should have enough gravity to hold on to an atmosphere, and the heat from its star could even power volcanic activity, belching gases like carbon dioxide into its sky. The stage was set. We had our Earth-sized world. We had our supreme instrument. Now for the moment of truth. What story was written in its sky? With the planet's existence and size confirmed, the science team turned to the main event, analyzing the transmission spectrum. This was the data that would reveal the atmosphere's composition. The anticipation was palpable. This wasn't just any observation. It was a glimpse into a new frontier. What would the first atmospheric reading of an Earth-sized world by the most advanced telescope in history actually look like? The possibilities were tantalizing. Scientists ran models of what they might find. Maybe a thick, hydrogen-dominated atmosphere, a primordial envelope of gas left over from the planet's formation. If so, the spectrum would show deep, plunging lines. Or maybe they'd find a secondary atmosphere created by the planet itself. A popular model for worlds like this is a dense, carbon dioxide-rich atmosphere similar to Venus. If LHS 475b had active geology, it might be spewing CO2, and JWST would see the telltale absorption signature of that molecule. A thick, methane-rich atmosphere, like that of Saturn's moon Titan, would produce a very distinct curve in the data, a strong signal, impossible to miss. Finding any of these would have been a landmark discovery. Proving that a rocky world this size could have any kind of atmosphere would tell us our theories about planet formation were on the right track. It would show that these small rocky worlds are active, dynamic systems. The team processed the data, meticulously cleaning the signal and plotting the results. The scientific community and the world held its breath. This was the moment we'd read the story of another Earth-sized planet for the first time. But what happens when you open the book and all the pages are blank? When the final spectrum for LHS 475b was unveiled, it showed something both baffling and profound. It was a flat line. Let that sink in. Across the entire range of wavelengths observed, there were no significant bumps or dips. No clear absorption from hydrogen. No obvious signature of methane. No telltale sign of a steam atmosphere. There was just a straight, featureless line, consistent with the planet simply being a solid sphere blocking starlight, with no detectable atmospheric gases to alter the light. The data itself was pristine, a technical marvel, but the result was a cosmic silence. The chemical whispers scientists were so eager to hear just weren't there. While an intriguing result, it immediately allowed researchers to rule out several possibilities. A thick, methane-dominated atmosphere like Titan's was definitively excluded. A puffy, hydrogen-rich atmosphere was also highly unlikely. The planet was, at the very least, not a gassy mini-Neptune in disguise. It was truly a rocky world. But the absence of these features opened up a perplexing mystery. First, the most striking possibility is that LHS 475b has no atmosphere at all. It could be a bare, airless rock like Mercury. Red dwarf stars can be notoriously violent, unleashing powerful stellar winds and flares of high-energy radiation. A planet orbiting as close as LHS 475b would be relentlessly bombarded. It's possible any atmosphere it ever had was simply blasted away over billions of years. The second possibility is more nuanced. The planet could have an atmosphere made almost entirely of heavier molecules, like 100% carbon dioxide. Counterintuitively, an atmosphere like that would be extremely difficult to detect. Heavy gases create a very compact atmosphere that doesn't extend far from the surface. The ring of gas filtering the starlight would be so thin that its absorption signature could be too faint to distinguish from a flat line with the current data. So, LHS 475b might be a secret Venus-like world. The third explanation is that an atmosphere is there, but it's hidden. A thick layer of high-altitude clouds or haze could be completely obscuring our view. These clouds would block the starlight uniformly across all wavelengths, preventing it from ever reaching the diverse layers below. The result? A flat line. If the planet has a CO2-rich atmosphere like Venus, it's very plausible it would also have thick clouds. So, we are left with a cosmic enigma. Is LHS 475b a dead, airless rock, a secret Venus, or a world hiding behind a wall of impenetrable clouds? The silence is not an answer, but the beginning of a much deeper question. The silence from LHS 475b is more than a scientific puzzle. It's a profound reality check in our search for life. For years, finding an Earth-sized planet was hailed as a crucial first step. We often assumed that, if you found a rocky planet of the right size, an atmosphere would likely follow. LHS 475b challenges that optimism. It tells us that being the right size might not be enough. A planet can be a near-perfect twin of Earth in diameter and still be a barren, airless world. This has huge implications for our search, especially around red dwarf stars. These stars make up about 75% of the Milky Way, so the vast majority of planets orbit them. Their habitable zones are very close in, which makes planets easier to find and study. But the silence of LHS 475b serves as a stark reminder. The very proximity that makes these planets great for study also makes them incredibly vulnerable to having their atmospheres stripped away by their parent star. What if the most common places to look for life are also some of the most hostile to it? This finding forces us to refine our search. It's no longer just about finding a planet in a habitable zone. We now understand more deeply that we must also investigate the history and temperament of its star. We have to ask, is the star too active? Has the planet been exposed to billions of years of radiation that would scour away its atmosphere? The case of LHS 475b suggests that many Earth-sized worlds around red dwarfs might be planetary husks. The silence we detected might be the default state for many similar rocky worlds. It's a possibility that makes our own vibrant, noisy, atmosphere-rich planet seem even more precious, and maybe even more of an exception. The story of LHS 475b is not one of failure, but of profound insight. The James Webb Space Telescope performed flawlessly. It confirmed an Earth-sized rocky world and showed it has the power to probe its environment. The flat spectrum it sent back, this great silence, is not an ending. It's a vital clue. It has narrowed down the possibilities and presented us with a new reality about the challenges facing planets. The mystery is far from over. Scientists have already scheduled more observation time for LHS 475b. By using other instruments on JWST, like the Mid-Infrared Instrument, MIRI, they hope to gather more data that could finally distinguish between a compact carbon dioxide atmosphere and no atmosphere at all. LHS 475b was just the first. JWST is now turning its golden eye to a whole host of other rocky worlds, each with its own story to tell. Some may shout with the chemistry of active geology. Others may whisper with the gases of a thin atmosphere. And many more might return that same eerie silence. Each result, whether a shout or a whisper, will teach us something new about our universe and our place within it. We began this journey looking for another Earth. What we're finding is a cosmos far more complex and challenging than we ever imagined. The silence of LHS 475b is a humbling reminder that we have only just begun to scratch the surface of understanding the worlds beyond our own. The search for answers, the quest to fill that silence with knowledge, continues, and the golden eye of Webb keeps watching.